Welcome back after the short tea break. Now we will proceed for the first technical session on track A for discrete algorithms and applications. This session will be chaired by Professor Urosh Sibes. Dr. Sibes is currently working as an assistant professor of computer science at the University of Ljubljana, Slovenia. He leads the Laboratory of Algorithmics, heading a team of 10 researchers. He has authored over 50 research papers and holds one US patent. His research collaborations span several industrial partners and focus on optimizing manufacturing processes, formalizing security protocols, and modeling combinatorial problems arising in real-world applications. His current research interests include combinatorial optimization, formal methods for security, and machine learning on graphs. Sir, we are really privileged to have you here today. So I will request you to hand over the session now. Now, in this track session, we have 5 papers to be presented with paper IDs 58, 16, 40, 36, and 22. Out of this, 36 and 22 will be presented online. Now, this is a gentle reminder to all the presenters that each paper will be allocated 12 minutes for presentation, followed by 3 minutes for Q&A. Please look out for the timekeeper. They will tell you about the time, and please adhere to the time limit. Sir, now the session is yours.
Okay, yeah, I got it to work. So thank you very much. The last session of the day is always the most demanding, especially for the audience. So you are the most with the highest endurance, the listeners. And for respect of your time, I will try to keep it short. And also for the presenters, I hope that we will keep the timing perfect. So the first presenter is Krishnendu Ghosh. This is his joint work with Jay Ball, both from College of Charleston. And he will be talking about his work in systems biology. So please, Krishnendu, the stage is yours.
Okay. Hello, everybody. Thank you. And the talk is bounded model checking for calibration of systems biology models under uncertainty. And I have no idea how many of you have any idea about all those words. So hopefully we will know about it as we go along. So some parts we have to do administratively. This research was funded by National Science Foundation, and my student was funded by Summer Research Grant. So what is the motivation for this work? Why are we interested in this work at all? The main motivation is that we want to build models such that biologists are able to know the answer for their queries. And the hard part is that it is impossible to build models from mere data. So what are the approximations that needed to be done in order to make a model that even has any semblance to answer the biological questions? So the data in biology is primarily from experimental data, and experimental data is very uncertain. You may perform an experiment over here in this room, and also the same experiment, if it is performed somewhere else, it may not yield the exact results. So that is the hard point. And also for the modelers, it is important to understand how robust is their model. So these are the main ideas that have spurred this interest in this domain. Some of the questions that a biologists want to ask, is there a pathway that generates a particular biochemical? Is there a biochemical X for the formation of biochemical Y? Is there a biochemical formed in some pathways but not in others? The idea that we want to address is what is known as a logic-based approach. And again, the hard part is how to build a reasoning mechanism using logic-based approach because of uncertain data. So here is the example that have spurred this research. So over here on A, you see there are some nodes and there are edges, A, B, and C. So if I have a chemical which has a value A1, and if it is progressing for a particular pathway X, A1, A2, A3. So those are the concentration of a chemical. But if you see B and C, the difference in A, B, and C is that B has less number of nodes. C has even lesser number of nodes. However, the only thing that is the same is the order of the pathways X, Y, and Z. So it's obvious that A has large number of states and C has less number of states. So it is always easier for us to handle computationally C. However, we lose out lots of useful information if we reduce the number of states. So here is the idea that we want to use. This idea is known as model checking. We construct a model, and in that model, we ask certain questions. Certain questions are the specifications. And if in that model, the specification is true, we say it is worked in that model, else it will give us a counterexample such that we find out where exactly we need to change. So this is the example that I always give to my students. So how you can use model checking in real life. So this example is of a railroad crossing. So when exactly there will be a railroad crossing would be blocked. If it is blocked, so it's obvious that the rail has to go through. But the blocking of that railway crossing, it must not be forever. So we build a model and we have a graphical structure and we label the nodes as A, B, and C. And then in that graphical structure, we ask questions. For all the nodes, if there is green and open, is it true? So we ask that on that particular model, and it will say yes or no. So this is the idea behind the research model checking. However, this is not that easy because it has this problem of what is known as a state explosion problem. So the state explosion means that if you increase the number of Boolean values, the number of cases that you have to check is exponentially large. So the way to circumvent this problem is to use bounded model checking, which uses SAT solvers. So coming back to our problem, we want to construct a model, and here we have in a vessel, we have lots of chemicals. So based on the rate of reactions, we construct that model. So R1, R2 till R8, they show that they are the chemical reactions that are modeled in that graphical structure. So here is the idea of bounded model checking. Software verification method uses a specific number of steps. Here the specific number of steps is the number of nodes that it can reach. Accepts a model specification and bounds the length of the path to check whether it is valid in that length of the path or not. If a counterexample is found, the specification is proven false and the program ends over there. If no counterexample is found, the program terminates upon the reaching the specific bound, yielding verified results. So this is the way that we construct a SAT problem, and then we try to feed it into the SAT solver to achieve bounded model checking. So I will skip over here and we go over in this slide. So this slide basically shows that if you have a pathway in A and pathway in B, pathway in A is much more finer because it has number of nodes which are extremely larger than pathway B. However, computationally, B is much more easier for us to handle. So this basically shows that in biological processes, when you are modeling it, there are biological process that takes 1 microsecond to execute, and there are biological process that may take an hour to execute. So how we can merge them in a system and we can query, that is the challenge. So a little bit of mathematics. We all know what is a graph, and in formal verification, we use a specialized terminology, which is a graph Kripke structure, but it is a graph with labeled nodes. And those nodes are labeled with atomic propositions. And once we have this model done, and then we can ask questions. However, over here in the Kripke structure, this is not a total structure. That means there is not a requirement that every node has to have a transition out of that node. So we use the word transition system, which addresses the totality of the system. And for our work, we use edge transition system, which has edge levels. So here are the standard definitions. AP is the set of atomic propositions. Yeah. Yes, they are the reaction.
The first graph, that means that reaction is every time changing the concentration.
Yes.
And then how do you replace 4 such things with this one or the different graph?
So over here, we say that instead of allowing a particular pathway or reaction to continuously execute like 0.5, 0.5, we say that it will execute 1. So we are having the number of nodes less.
So maybe in the same type of reaction, instead of saying that there are 4 repetitions,
Yes.
I plug them the level as 1.
Yes.
Sorry for disturbing you.
No.
Please.
Just a
That-
bit of timing,
That's actually good. At least you are awake.
just a bit of a timing warning. It's just 1 minute left, so.
Okay. So we have this standard definitions, and we use this definitions to show that how we can find out in a path if there is a node that changes the pathways. Going over here, and we have actually modeled this pathway, RKIP pathway, and those M1, M2, M9, M10, and M7. It means that those are the concentrations that are actually there, and all of the other ones are formed in the process of the reaction. So we construct the model, and then I think I should go over here. We use this sample queries to find out how fast it is. So we found that if we actually increase the size of the path, everything is pretty good. Everything is executed within a second. So we have also the idea of coarse and fine model. Coarse means model that is compressed. Fine means the model that has a lot of nodes. So we have, so in this work, we use the idea of bounded model checking. We have used the concentration symbolically, and we have used the idea of pinpoint interval, which means we have considered only the midpoint of the concentration interval for our computation, and we are exploring the idea of quantified Boolean formulas. And I want to go over here. So this is the first work in this direction, but we also know that biological systems are stochastic and also multi-scale. So we are actually addressing the idea of concurrency as well as stochastic as well as uncertainty in our next work. Thank you. I think
Thank you for your presentation. We're a bit short on time, but is there any questions?
nobody has any questions.
Yeah. So a short question from me. So bounded model checking is basically when you cannot prove the whole thing.
Yes.
Are there any properties that you actually try to prove the whole thing?
So bounded model checking is a faster way to do model checking. That was the focus of this work. And we wanted to check whether certain concentration appear in certain paths of length A,
Okay.
1 to 4 or 5, etc.
Thank you very much. Let's
Thank
thank the speaker again. So the next speaker will deal with software defects. So this is the speaker is Reshmi Maulik, and joint work with Subhajit Datta. Okay, so Reshmi.
মানে এটা যদি উপর হাতে না
ওটাও দুটোই আছে ম্যাম, এটা কাইন্ডলি নিয়ে নিন। আপনি এটা আপনার জামা একটু লাগিয়ে নিন, এইরকম মুখ থেকে এইটুকুনি ডিস্টেন্সে লাগাবো। হ্যাঁ, আর আপনার পকেটে ম্যাম ওটা একটু আপনার পকেটে একটু বড় আছে।
Let's wait for the technical team to prepare the speaker. Reshmi,
Yeah.
please.
So thank you. So good afternoon. Today I am going to present our paper, The Curious Case of Complexity exploring causal influences on software defects. So this is the plan of our presentation. The structural complexity of the software is always an area of research, as it is a key determinant of quality that affects the software. And most of the existing studies that are currently available are correlational in nature. We'll study the complexity and the defect. We are trying to find a causal relationship between the complexity and defect, and it will provide an insight for the developers and the managers so that they can early detect the area where they can concentrate and can minimize the software defects. So our objective is to discover the causal effects of essential complexity and design complexity on the number of defects after accounting for other peripheral influences like effort, difficulty, and intelligence quotient. So these are all the related works in this field which are related to GS, the greedy search algorithm we will be using, and the defect area, but all those are correlational in nature. None of them has dealt with the causal analysis. So there is limited causal studies in the field of software complexity research. So I hope this is the pioneer work in this field. So causal discovery using greedy equivalent search algorithm, this is the methodology we will be following. We will be constructing a causal directed acyclic graph from the knowledge we have gained from the GS algorithm. Then we will go for the causal inference and make the validation check. Then we interpret the results we have obtained using our domain knowledge. So greedy equivalent search algorithm for causal discovery involves three main steps. First of all, we'll start with an empty graph. Then we'll keep on adding edges based on the BIC score, which is an essential score for model selection. And after that, we'll backward FIs will keep on removing edges to optimize the model, but we'll keep on check that the score is still increasing. And efficient search will be made over the Markov equivalence classes. For this research, we have used the KC1 dataset from Promise repository. This is a well-used dataset from NASA for defect prediction, and it derived for a storage management system used for processing ground data. It has got 2,109 rows and 22 columns, which we can use as metrics, and it has got columns for McCabe and Halstead complexity measures. These are the model variables we are using. These are 7 variables. First one is the essential complexity, which define the unstructuredness of code. Then we have got the design complexity that show the program's control flow. Then effort estimate that needs the mental work to write or maintain the code. Then intelligent quotient reflect how efficiently the program can be expressed. Difficulty measures how hard is the code to understand, and LO code means the line of executable code, the codes which on running can take action. So these are the two models we have obtained using the greedy equivalent search algorithm. First one is the effect of essential complexity on the defects, and the second one is the design complexity effect on defects. On the first figure, we can see that D is for difficulty, I is for intelligence, and E is for effort. All of them has got an effect on the essential complexity, EV underscores G, and that line of code is also has an effect on the essential complexity, which in turn has an effect on the defects. On the other hand, when we go for the design complexity, we see that the defects is only affected by the intelligence and difficulty, and it is neither affected by the effort nor by the design complexity. So to validate our model, we have used three type of refutation technique. One is random common cause, another one is data subset refuter, and third one is placebo treatment. Placebo treatment is nothing but if you don't give any type of treatment, means if we are not considering any particular treatment, then this is known as placebo treatment. It will help us to understand whether actually the treatment we are doing is putting any effect on the variable we are considering or not. So these are the research results we have obtained. So here we can see that the essential complexity has got an effect on defect, and it has got a negative effect. You can see. So there is an inverse relationship. So you, as we recall, that essential complexity means unstructuredness in the code. We see that the more it is structured, it should be better. But now we find that there is an unstructuredness in the code, and if there is unstructuredness in the code, then it is better, because more you are getting to a structuredness, you have to, you are more getting into the structured way, and there the possibility of defect will increase, because you have to get into the framework of that particular software. Whereas in the case of unstructuredness, we can be aware of it. And also we can see in both the tables, there is an effect of difficulty and intelligence on the defect. Both the results coincide, and also that validation by random common cause and dataset refuter coincide with the values we have obtained as a causal estimate. So it validates our model. And the placebo treatment is almost equal to 0. This shows that our treatment has got this effect on the defect. As far as the construct validity is concerned, we have used a peer-reviewed source. So and also we have used a single GS algorithm. So this may have a limited construct coverage. As far as the internet validity is concerned, we have used historical data, which is already being used for several researchers. So there should not be any selection bias or maturation effect. External validity, the present study is analyzed on a single data set, so it can't be generalized. And as far as the reliability is concerned, our results can be replicated as the data set is publicly accessible. So we find that design complexity and essential complexity behave differently, and the statistical evidence shows that only the essential complexity has got its effect on the defect and not the design complexity. And also the intelligence quotient content and the difficulty level has got its effect on the defect, but not the effort for the design complexity. So we hope that our results will help the practitioners and managers to get the defect solved at its earliest. Thank you.
Okay, thank you very much. We have time for questions.
Sorry, I missed the beginning. What are the things that decides the essential complexity of your software?
Sir, essential complexity itself is given a metric. A metric is given in the data set, EV_G, that calculates the essential complexity. It is given in the data set.
But they didn't explain on what they decided. There must be some criteria on which that number came up, right?
That I have derived it from the data set. We have done the causal analysis and then we got the value.
No. What I'm saying is, what is the physical significance? Design complexity, I understand. What can be a design complexity of a software? But what is the essential complexity of
unstructuredness of the code?
Unstructured. So the more unstructured it is,
The
more complex it is.
no. No, the more structured it is, more complex it is.
So that's what you say.
Yeah, it is other way around. The more we unstructured it is, that is the essential complexity. Unstructuredness of the code. The
By
more
structure, what does it mean?
Sir, suppose we can look for the Django. Django has got its own framework. But earlier where we used to code, there is no such framework or no such structuredness. So that is the difference. The different type of softwares, the more we are getting into the structuredness, the greater is the problem, because there is a problem in understanding the structure, and the problem defect may arise from there.
Okay, thank you. We have another question. So,
Yeah, so there's a lot of work on log-based methods and causal discovery software. And have you compared methods, personally, I have experimented and have seen like GS takes time. There are data methods like Peter
Sir, this is means something perceptional. Somebody thinks PC is better and someone says G is better. There is also fast GS algorithm, many several, yeah. Yes.
So have you applied those?
Sir, speaking frankly, if you apply different algorithms, it will give you different graphs. And according to the graphs, the result will also change. Yeah, that is the problem. So you have to stick to someone that you can rely upon. So GS is something that I have relied upon, and it's giving me fruitful results.
So
I have not done any comparison.
another question, yeah.
Short question. So, do you think that the olden days there was no concept of structured programming and structured code? So those codes are better performing than the present-day structured codes?
Sir, your answer is in your question, I think. Because still now, till date, we are using the compiler, interpreter all on the previous languages, not in the newly developed languages. So the answer is in your question, I think.
Okay, thank you. Any other questions? So I have a question which is related to, so all the code that you use for the benchmark, this is the same language, or what kind of tools were used?
Sir, I have used the Python. Python there, I have used UI library.
Not your code, but the code that you evaluated. Was this from of the same language or a different
Sir,
language?
I have used the that KC1 dataset from the NASA, that already available, publicly accessible. I have not generated that.
So you don't know what languages?
I don't know actually.
Okay, so the last question. So you mentioned that this would be a nice tool for decision making for software development.
Yes.
Do you have any, let's say, guideline which you can draw from your results for someone that does software development?
Sir, what I find that if you go for essential means unstructuredness of the code, then it will be decreasing the defects. And if you go for the design complexity, it has got no effect at all. These are the two results I have derived till now.
Okay. Thank you very much. Let's give an applause for the presenter. Okay, the third presentation for today will be given by Suman Sanyal from Goa Institute of Management. We move into computer graphics, right? So the title of his talk is Convexity-Driven Projection for Point Cloud Dimensionality Reduction. So let's wait for the microphone to be plugged.
Hello?
Hey, so Suman, please.
All right, thank you. So what I want to talk now is about a dimension reduction technique which would retain the convexity of the data set. So we have various kind of dimension reduction technique. The most common one is the principal component analysis, in which the covariance structure or the spread of the data set is retained. So what we thought, or what I thought, was that is it possible to retain the geometric structure or some of the geometric structure in the data set while we do the dimension reduction? And with that, this particular technique will retain the non-convexity of the data set. So the key idea is that if we have a point cloud, we construct a graph with that point cloud, KNN graph. And then the idea is that the Euclidean distance between any two nodes is always shorter than the shortest path between the two nodes. And the ratio between them can be used as a measure of the convexity. So that is what will get used in this algorithm. So using that, we construct a positive semi-definite matrix. After that, the algorithm kind of goes like the principal component analysis. So we calculate the eigenvalue, select the largest eigenvalue, and then construct the projection matrix. So in the first half of the algorithm is where all the tricks happens, and which is where we invoke the convexity part of the data set. So if we look into the various dimension reduction technique, so we have the PCA, LPP. A PCA will target the variance. It would want to retain the variability in the data set. It's a linear dimension reduction technique. We have then the LPP. So each of these dimension reduction technique, they have a particular kind of a target. Whenever a dimension reduction happens, some kind of information is lost and then some kind of information is retained. The kind of information we want to retain actually defines what kind of dimension reduction technique it is. In our case, which is the CDP, what we want to target is the detour or the convexity part of the data set. So steps are the following. Suppose we are given n points in d-dimensional space. We calculate, we construct a KNN graph with Euclidean edge weights. We take the weight and then we have the shortest path. We define the detour ratio as the ratio between the Euclidean and the shortest path. It will be always between 0 and 1. Now we introduce a hyperparameter which is the tau, and we consider a pair as admissible if the detour ratio is smaller than or equal to tau. Now this is something which we can change at the time of the experiment as well, and it gives rises to different kind of reduction which we can see. So we have the shortest path, we have the Euclidean distance, and If the shortest path is much larger than the Euclidean path, then that particular pair is detour revealing. It can actually find out if the point cloud has any hole, or it has any wall, or if it has any obstacle or not. Because if it has any obstacle, shortest path has to go around it. Even if it has a hole inside the point cloud, the shortest path had to go around it, making it longer than the Euclidean distance between the 2 points. So we have a direction for each pair, and then we use the detour strength weight. And with that, we construct our PSD structure matrix. Once we have the PSD structure matrix, the rest of the steps are very similar to principal component analysis. So we find out the eigenpair, we pick the largest of these eigenvalues and construct the projection matrix. We multiply and we get the point cloud in the new dimension. So this is what this convexity driven projection is. So the algorithm would look like this. We start with the point, you fix a target dimension. KNN, once again, you need to fix a certain kind of threshold. We construct the KNN graph, compute the shortest path, form the admissible set, build the positive semi-definite matrix, eigenvalue, eigenvector, a projection matrix, and you transform the data. So we have basically two hyperparameters which are used in this algorithm. One is the threshold tau, and the other one is the KNN. What is the K of the KNN graph? So these two. It's the unit vector. Unit vector. It gives you the direction. It is a transpose.
The line 5 supposed to be UI square. Yeah, sorry.
Okay. So two hyperparameter, one is the tau, which is smaller. If the tau is smaller, which means fewer but stronger detour pair. If that is large, then more pairs closer to variance like behavior. KNN small means longer path, stronger detours. Large means shorter path, weaker detours. So these are the two things. When you actually carry out the experimentation, you can manipulate them, and you can get different kind of a projection. So I have worked out in the paper, you can see I worked out a small example with only 5 points where I have transformed from dimension 3 to dimension 2, and I have worked out in detail exact all the steps of the calculation. and it gives us the projection. It works out very well for the smaller number of dimensions, smaller number of points, to the extent that we can actually work it out by hand. So this, I think any undergraduate can understand what has happened here. You don't need any big mathematical tools to understand this. It can be actually worked out. Okay. So limitations, of course, we know that shortest path, once it goes in the high dimension or for large n, is computationally very intensive. Then the quality of the graph matters. It depends on the hyperparameters. Sometimes you may not be able to find a path at all. And finally, my hunch is that since CDP is linear, it might not be able to unfold this highly nonlinear manifolds in high dimension. It may not be able to do so good up there. So that's my hunch, even though experiments are still on the way. Now, among the future direction, I have a lot, but the one which I am really interested is the task-aware variants, where can we do a dimension reduction in such a way that helps in the downstream planning or the segmentation? So can we do, usually in ML, first we do the dimension reduction and then we do the task. But in this case, I was thinking if we can actually do the dimension reduction based on this particular task or not. So that's something which I would like to work on. And these days, geometry of the data has become, like in the last few months, has become a very big deal. From the LLM where we do this stuff, where we do the stat, now we want to look into the geometry. So here is the conclusion. Convexity-driven projection is a linear dimension reduction, and it gives us, it helps us preserve the non-convexity of the data set. So that's all from my side. Thank you.
Thank you very much for a lovely presentation. Any questions? Yeah, so.
How do you contrast this with Johnson data stress?
Right. So I was also thinking the same thing. Do random projection be able to preserve the non-convexity or not? So Johnson, Linden, Strauss, I see some connection, but I actually don't know the answer to that, whether random projection itself will be good enough or not. In the high dimension, something could happen. In the low dimension, my hunch is that it might not be able to retain.
There are theoretical properties that in terms of distance of the groups of Johnson industry.
Yeah.
In terms of distances, it can put some. It's a flexible. Convexity for that.
Yeah, in the convexity, I have some results from the theoretical where I can actually show that convexity has been retained, which is included in the paper. So it gives me the bound as to how much convexity has been retained in the way in which we define. But that is something which I would also like to explore, whether a random projection itself will do the job or not.
Okay, any other questions? If not, let's thank the speaker again.
Thank you.
And we move to the final two presentations. Both of them will be online. So I guess the technical team is preparing for the next two presentation.
Yes.
So the first one will be given by the researchers. The researchers from Warsaw University and Lund University and Malmö University. The presenter is Miroslav Kowaluk, and the title will be Approximate All Pairs, Hamming Distances, and 0-1 Matrix Multiplication. So let's wait for the technology to start working. Let's see if there's.
What's that? Yes, sir, she's already here with this one.
So Miroslav? No? Can you hear me? Unfortunately, we can't.
I can hear you.
You hear us now?
Yes, I can hear you.
So the presenter, Mia, you will be presenting the paper.
Yes.
So I was giving another name here. So Mia Persson from Malmö University. Please, can you share the slides and then start with the presentation?
Yes.
You'll be given 12 minutes, and when there are 3 minutes left, I will tell you, okay? So
Yes, thank you. Yes, thank you very much. The title of our talk is Approximate All Pairs Having Distances and 0-1 Matrix Multiplication. Co-authors here are Miroslav Kowaluk of University of Warsaw, André Lingas of Lund University, and myself, Mia Persson of Malmö University. Consider 2 points in d-dimensional standard Hamming space. That means there are 0-1 vectors, or more generally, 2 points in generalized Hamming space. So the difference that instead of 0-1 alphabet, we can have some larger but still finite alphabet sigma. Then we define the Hamming distance between 2 such points as the number of coordinate positions on which they differ. The problem of computing all pairs Hamming distances for a set of points in a generalized Hamming space is a frequent major step in hierarchical clustering with many applications in medical science, machine learning, and it is quite often used in the construction of evolutionary trees. In 2018, Arslan presented an algorithm for computing all pairs Hamming distances in a generalized Hamming space. His algorithm reduces this problem to computing a finite number of arithmetic matrix products for related matrices. And it runs in time proportional to the size of the alphabet sigma times n to omega, where n is the number of input points and omega is the exponent of fast arithmetic matrix multiplication. Our first result is a reverse reduction. So more specifically, we have two matrices with 0, 1 entries of size P times Q and Q times R respectively. And we assume that we are giving the Hamming distances between each row of the first matrix and each column of the second matrix. Then we can compute the arithmetic matrix product of these two matrices in time proportional to the size of the input matrices plus the size of the output matrix. And the idea here is very simple. So let us denote the number of ones in a vector with this exponent 1. And consider now two one-dimensional vectors A and B. Say 0, 1s vectors A and B. Then their inner product is easily seen to be equal to the number of ones in A plus the number of ones in B minus the Hamming distance between them. Everything divided by 2. So now if we just consider an entry of the arithmetic matrix products of these two matrices corresponding to the ith row of the first matrix and the jth column of the second matrix, that means the value of the entry is the inner product of this row and this column. So we write it on the left side and we can rewrite it as the sum of the inner product or products of one-dimensional vectors induced by consecutive coordinates and plug in our formula. And so finally, we get the formula that says that the value of the entry is just equal to the number of ones in the ith row of the first matrix plus the number of ones in the jth column of the second matrix. Minus the Hamming distance between these two vectors, everything divided by 2. So now it is enough to compute the number of ones in each row of the first matrix and the number of ones in each column of the second matrix. And given the Hamming distances between each row of the first matrix and each column of the second matrix, and giving the Hamming distances between them, we can easily obtain the arithmetic product of these two matrices. Yes. Next, we will provide an approximation algorithm for the problem of computing all pairs Hamming distances. And as a tool, we will use here a so-called randomized dimension reduction in the spirit of the famous Johnson-Lindenstrauss reduction. We use here a variant due to Icaa from 2003. So very roughly, suppose that we have a set of n points in d-dimensional real space and let us fix epsilon. Then we can set the dimension of the subspace to which we shall map the points to a dimension k not greater than some constant times log of n divided by epsilon squared. And now let us take a random matrix of dimension k times d such that for each entry of this matrix, the entry is set to 1 with probability half and to -1 with probability half. Then the random matrix induces a mapping from this, our origin R to D space, to its subspace R to K, such that if we take any pair of input points, then the squared L2 distance between images of this point under this mapping is within 1 minus epsilon, 1 plus epsilon of the squared L2 distances of the original points with high probability. And now we have the following observation outside this fact. Suppose that our points are 0, 1 vectors. Then the observation is that the squared L2 distance between such vectors is just the Hamming distance between them. So in this way, we can approximate the Hamming distance between each pair of the input points by taking the square of the L2 distance between the images of these points under the mapping, and the approximation is within 1 minus epsilon, 1 plus epsilon with high probability. So this is the basis of our simple algorithm for approximate all pairs Hamming distance. So we can conclude that, say, if we fix some non-negative epsilon not greater than half for our set of n input points, we can provide approximation of the Hamming distances between them with the factor 1 minus epsilon, 1 plus epsilon, and this can be done in time proportional to n squared plus n times the dimension, and this sum multiplied by log of n divided by epsilon squared. Importantly, we assume that these points belong to standard d-dimensional Hamming space. Now we can consider a graph where the nodes correspond to the input endpoints and an edge between two such nodes is equal to the approximate Hamming distance between the endpoints. This approximate distance provided by the theorem. And now we can simply run Prim's algorithm for minimum spanning tree on this graph, and we obtain in this way an approximation algorithm for minimum spanning tree of n points in standard Hamming space, d-dimensional, with approximation guarantee, which is 1 plus epsilon divided by 1 minus epsilon, and the asymptotic running time is here the same as in the theorem. That means n squared plus n times d, everything multiplied by log of n divided by epsilon squared. In the next session, we provide an approximation algorithm for the arithmetic product of 0, 1 matrices. Simply, we combined our reduction of such arithmetic product to the problem of all pairs Hamming distances with our approximation algorithm for the problem of computing all pairs Hamming distances. And in effect, we can, if we again fix some epsilon, provide approximation of the arithmetic product of two 0, 1 matrices of size n by n, such that, say, entry of the product corresponding to the ith row of the first matrix and the jth column of the second matrix is approximated within an additive error of at most epsilon times the minimum of the Hamming distance between the ith row of the first matrix and the jth column of the second matrix and complement of the Hamming distance. And this can be done in time proportional to n squared times log of n divided by epsilon squared. Our final result is an exact algorithm for the minimum spanning tree of n points in generalized Hamming space. Our algorithm is output sensitive and it runs in time proportional to polylog of n times the sum of n plus dimension d plus m, where m is the cost of minimum spanning tree of these points. So the smaller is the m, the faster is our algorithm. Thank you very much.
Much, Mia. Any questions from the audience? Questions? I have one question.
Yes.
Have you did any empirical results, or have you tried if it how it scales and how it works, or you have only theoretical results?
We have only theoretical result at the moment, but it's a very interesting open problem to consider also to try to implement this.
You use the Hamming distance as somehow some help to obtain the product, right?
Yes.
That you could use that would be helpful.
Yes, it will be helpful. Yes.
But you did not consider other matrices. It's the Hamming distance.
No, we just consider the Hamming distance at the moment. So, but it's interesting open problem also to consider other as well. Definitely.
Thank you.
Mm.
One question from the audience. Where is the microphone? I don't think so. Yeah, the microphone is coming. Just a second.
Mm.
Related to earlier question, if you generalize the Hamming distance, how will the results for generic distance, right? Can you hear?
Could you please repeat the question? I cannot hear, unfortunately.
If you generalize the Hamming distance,
Mm.
how the theory guarantee psychology no?
Can you hear me?
I unfortunately cannot hear. Perhaps can you please send an email with the question and we will respond, because I cannot hear, unfortunately.
We lost your audio now again. So yeah, we can put this offline and postpone this question for. So thank you again, Mia. Let's give it a round.
Thank you very much. Thank you.
Okay, now the last presentation for the day. Do we have who is the presenter? So Amol, it's you. So the last presentation will be given by Amol Narke. Yeah. And the topic is an efficient algorithm for path matrix computation and improved path energy bounds. So, Amol, can you hear us?
Yes, sir. Yes, sir.
At
Am
the
I
moment,
audible?
we cannot.
Yes, sir. Am I audible to you?
Oh, we still cannot hear you.
Now, sir?
Yeah. Okay, so Amol, please, you have 12 minutes, and after 8 minutes, I will just give you a little warning to tell you the time.
Okay, thank you. Thank you so much, sir. So, good afternoon, all. I am Professor Amol Narke, working as an assistant professor and research scholar in the Department of Mathematics and Statistics, MIT World Peace University, Pune. This is the joint work done with my supervisor, Dr. Prashant Malvatkar. The title of my talk is An Efficient Algorithm for Path Matrix Computation and Improved Path Energy Bounds. So in this talk, I mainly contributed into two parts. One is an faster algorithm to calculate a path matrix and new and sharper bounds on path energy of graphs. So outline of my talk is I will begin with an introduction, then the computation of path matrix, followed by an illustrative examples. Then I move forward towards the bounds that already exist and the bounds that we have obtained, then comparison with these two bounds, then conclusion and references. So let me start with an introduction and motivation. So adjacency matrix A of G of a graph G is of a graph G with the vertex set V and edge set E is n cross n 0, 1 matrix which gives us an adjacency among the vertices. And the eigenvalues of this matrix we called as a spectrum of an adjacency matrix. The graph energy was introduced by Gutmann in 1978, which is the absolute sum of its eigenvalues. The graph energy has various applications in chemistry, physics, network theory, and many more. Motivated by this spectral approach, Patekar and Shikare in 2018 derive a path matrix P of G, which gives us its ijth entry represents a maximum number of vertex disjoint path, which are internally vertex disjoint paths between vertices Vi and Vj. And we have calculated its energy by taking its absolute sum. Let us understand this by an example. So here we have a graph G, middle we have an adjacency matrix, and here we have a path matrix. One can easily check the entry 1, 3 is 0 in adjacency matrix. It means there is no edge from vertex 1 to vertex 3. But in the path matrix, 1, 3 entry is 2. It means we have total 2 number of vertex disjoint paths from vertex 1 to vertex 3. One can find 1, 2, 3 is the one path and 1, 4, 3 is the another path. One can find more paths just like 1, 2, 5, 3. This is also one path, but which is not a vertex disjoint. That's why we have taken just 1, 2, 3, or one can take 1, 2, 5, 3, one of them. Okay. Then we have calculated its spectrum, the adjacency spectrum and the path spectrum. And for the path spectrum, we have taken its absolute sum. We get an energy which is approximately 21.37. Now we move forward to find and path matrix algorithm for a path matrix. Leak and others in 2018 given an algorithm to find out the path matrix with time complexity big O of cardinality of E into cardinality of V cube, which is computationally expensive, particularly for a dense graph. So we overcome this limitation by constructing Gomuru-Hue tree and vertex split network, and then we apply a Dinic algorithm to find out a path matrix. This approach enables efficient computation for all pair of vertices using unit capacity max flow routine, leading to improved overall time complexity, which comes to be big O of cardinality of V into cardinality of E into square root of cardinality of E plus cardinality of V square. So let us understand algorithm. My algorithm has 4 important steps. We begin with a vertex split reduction. In that, we convert a graph into a unit capacity flow network. So each non-terminal vertex V is replaced V in and V out. So let us see an example. So here we have a graph G. I just consider a vertex with label 0. So here 0 is split into 0 in and 0 out with one capacity. And each undirected edge UV is replaced by directed arcs U out to V in and V out to U in. So one can check here. So I can take an edge 1, 2. So 1, 2 is replaced by 1 out to 2 in and 2 out to 1 in. That's how one can find a vertex split network. Then we build a Gomuru-Hue tree constructions using cardinality of V minus 1 max flow computation. So each flow is computed using Dinic algorithm. And thus we get our total cost big O of cardinality of V into cardinality of E into square root of cardinality of E. After that, we reprocess tree T to support a constant minimum queries along any path using a big O of cardinality of V into cardinality of V times. And lastly, we extract our path matrix where its entry Pij is nothing but the weight of an edge on a tree whose path joins vertex I to vertex j. And by adding this all complexity, we get our time complexity big O of cardinality of V into cardinality of E square root of cardinality of E plus cardinality of V square. So let us understand this by taking an example. Here I have taken a very simple graph, a triangle with one edge added to vertex 2, graph G. We convert this graph into vertex splitting network of G, and then we construct a Gomuru U tree of a graph G. Here a vertex 0, 1, 2 forms a triangle. The vertex connectivity is 2. Now if we want to find how many vertex disjoint paths from 1 to 2, so we are going to find a minimum weights, that 2 defines a weights of an weights, or you can say a minimum vertex ket in a Gomuru U tree. So from 1 to 2 we have here 2 weights, from 1 to 0, and 0 to 2 we have 2. The minimum is 2. Thus we get 2 internally vertex disjoint paths, and one can cross check in a graph itself. So one is directly a edge via 1 to 2, and another is edge 1, 0, 2. So this is how one can compute a path matrix. And the connectivity K of UV is nothing but the minimum of weight on an tree by joining an path from U to V. So this leads to our main correctness theorem for computing a vertex disjoint paths. The following theorem says that for a graph, for any pair of vertices UV from a vertex set, the algorithm computes a vertex connectivity, that is a maximum number of internally vertex disjoint UV paths in a graph G. Thus, the algorithm correctly computes the entire path matrix. Now, I move forward my discussion towards a bounds on a path energy. In 2018, Shikare and others proposed a conjecture saying the maximum energy for any graph, the maximum path energy for any connected graph is 2 into n minus 1 square, and the equality holds when your graph is a complete graph over n vertices. In 2019, the leak proved that conjecture and given a proof that this is holds. Although the bound is sharp for a complete graph, but in general, it is not good for non-complete graphs. Significantly, this bound overestimates the actual path energy. This motivates us to find a sharper bound that reflects a graph structure more accurately.
3 minutes.
So in the following, yes, sir. Yeah. In the following proposition, we establish a row sum. So this proposition gives us for any graph G, its path matrix has a path matrix, row sum of a path matrix has upper bound n minus 1 into degree of V. And by using Georgian type algorithm, one can find an absolute value for path eigenvalue in terms of maximum degree. And the upper bound is n minus 1 into delta. So this proposition and lemma gives us an upper bound for an row sum and upper bound for an eigenvalue. Now to find out a new bound, we consider n plus n minus and n0 are the total number of positive, negative and zero eigenvalues of a path matrix G, and mu is nothing but the minimum among them. Then we have obtained the theorem which says let G be a graph on n vertices with path matrix P of G, and mu is nothing but the minimum number of positive, negative eigenvalues of path matrix G. Then the path energy of G has upper bound 2 into mu into n minus 1 into delta. But when mu is equal to 1 and delta is equal to n minus 1, that is nothing but the maximum degree in a graph, this bound is exactly as per the classical bounds. But when mu becomes more than 1, this bound is not good enough. Thus, this motivates us to find out a new bound, and that new bound we have obtained by using Frobenius norm that given in the below theorem. So let G be a graph with a path matrix P of G, then path energy of G is less than or equal to 2 into square root of mu over a Frobenius norm calculated over a path matrix. And this bound remains effectively across a wide range of graph classes. So I have taken the 10 graphs. These are arbitrary graphs I have taken. Then I have
Sorry,
found
we
out,
lost you a little bit.
am I audible now?
Here again.
Okay, yeah. So I have taken 10 different graphs and I have calculated its actual path energy, a classical bound given by Shikare 2 into n minus 1 square, later proved by Lick, then the spectral bound that we have obtained in this paper with the maximum degree and the Frobenius norm in terms of Frobenius norm. So by using this, we have plot the graph. Here, the red one is nothing but the classical graph, the green one that we have calculated in terms of degree, and the brown one we have done by using a Frobenius norm. So one can easily check the actual path energy and the brown graph are very close to the actual values. And lastly, we have obtained a relationship between energy of a graph and path energy of a graph, and this given in the below theorem. So let G be a connected graph on n vertices, then energy of a graph is less than or equal to n divided by 2 into path energy of graph. The conclusion: in this paper, we concluded an efficient algorithm to computing all pairs path matrix. We have established a spectral and Frobenius-based norms. The Frobenius-based norm is provide uniform sharper estimate for all graphs except the complete graphs. Overall, this works improves both computational efficiency and theoretical understanding of path energy. These are the references that I have used throughout my presentation and the paper. Thank you. Thank you so much.
Thank you very much, Amol. And the audience has any questions?
Yes.
So this was the last presentation of this session, and the audience is already tired. But so I have a very short questions. Can you hear me?
Yes, sir. Yes, sir.
Matrices that you showed in the end, were they taken from some realistic applications, or you generated them?
I have generated by using any random approach one, and also I have calculated by using naughty graph. There is a one collection of graphs, and I have checked my all the results. This gives me a good one. So these are the random graphs that I have taken.
But do you have any estimations of this Frobenius bound?
Yes.
How the realistic graphs have small value or large values of this?
So I have checked for so many graphs near about I have a collection of data sets. From that data sets, I have found out whatever the bound I have found by using Frobenius one, which is always sharper than the previous two bounds. That is nothing but in terms of maximum degree and the classical upper bound. Okay. And we have compared them also.
Thank the speaker again.
Thank you. Thank you, sir.
Thank you, sir, for chairing the session so nicely. I would request Professor Shubhashish Mojumdar to felicitate Dr. Sibej. Please have a round of applause for him. Dear all, on screen you can now see the QR code for the feedback of day 1 of Icaa 2026. So kindly give your feedback. This will serve as great motivation for us for the coming years. And dear participants, please note that this feedback will also suffice as your attendance for day 1. So kindly do the needful. So dear all, this brings us to the conclusion of a very enriching day 1 of Icaa 2026. We sincerely thank all the dignitaries, speakers, chairs, and participants for their valuable presence and contribution today. We look forward to welcoming you back tomorrow at 9:15 a.m. at the same venue for another enriching day day 2 of the conference. Till then, good night and thank you once again.